Okay, so this is homework question number 7, where the rancher wants a rectangular field with a fence down the middle, splitting it in half. I don't think the half is significant. That X could be anywhere, but we know the area needs to be 2 million square feet, right? Feet squared. So that gives us 3 X's and 2 Y's for the length of fence he needs. That seems correct. Okay. So solving for y and substituting, we now have L as a function of x. And clean that up a tiny bit to be 4 million over x plus 3x. And then we want to take the derivative of that. Okay, so dl dx would then be negative 4 million. Hi, Sarah.
Hi, Gary.
Over x squared, right?
We're not late. We just started. Okay.
Plus 3. Yeah, we just started early on a homework question Rob had. What's up?
So during your office hours,
can you hold off on that question?
Yes.
Okay. I think I got that right. Any objections about my derivative? Does it look good? That looks right. All right, so let me set that sucker equal to 0. And we'll get negative 4 million. No zeros yet. There we go. Over x squared equals negative 3. And then we multiply by x squared and divide by 3. So then x squared is going to be whatever 4 million is divided by 3. No zeros, yep. So x is the square root of that. Three, 1, 2, 3 over 3. And do I really care about cleaning that up? Oh, that cleans up kind of nice. That's 4 million is the square of 2,000, isn't it? No? Someone check that for me. Calculator. If I take 2, 1, 2, 3 and square it, I get 1, 2, 3 zeros. Yeah, that's right. Okay. So not that it matters. Usually I don't bother cleaning these up in an applied problem like this. I just throw it in the calculator from here. So I'll do that next. Anyway, if you wanted to reduce this, this would be 2,000 over the square root of 3. And rationalizing the denominator is kind of silly, so I don't bother with that. So then y is 2 million over x. Or I could multiply by the reciprocal of x. So then y would be 2 million, 1, 2, 3 times the reciprocal of x, which would be the square root of 3 over 2,000. And that cleans up a little bit, right? Some zeros go away. 2 goes into 2 once. So I get 1,000 square root of 3 for y. Change color.
Wait, did you plug? Wait, what'd you get for y?
Oh, I never actually did that. So up here, if you solve this right here for y, you get 2 million over x. So I was just thinking that. Sorry, I should have wrote that down.
Y squared is 3.
So this is your y right here. So then y is 1,000 square root of 3. X is 2,000 over square root of 3. And then we throw them in there and see what we get. Okay, so let's do that next. Does this match what you got, Rob?
No.
You had an error in here? Okay, or I do, right?
No, I did.
Oh, you definitely found
I
it?
plugged everything in.
Okay, so I like this one. So I'm just going to double check with calculator. Let's see, how am I going to double check this one? So we had 2 y's, right? Yeah, so 2 times 2, no, 1,000 square root of 3. Was y. And then there's 3 x's, and x was 2,000 over the square root of 3. Is that correct? Okay. So if I type that in right, then the length of the fence, the least amount of fence we can use would be 6,928.2 feet. Is that the right answer, Rob, according to your?
Yeah, that's exactly it.
That's the one? Okay. So just a note on these kinds of problems. I almost always have to draw a picture to solve it. That helps me get my brain going, right? And then you're usually going to have to get multiple equations to kind of whittle it down so you have a function of a single variable. And then once you have that, then you can take the derivative, set it equal to 0, solve, and backtrack. Usually in the last few examples I did, I never bother cleaning things up like this. I don't know why I did it today. It just seemed like fun. It's kind of like biking up a hill is fun. Usually I just plug right into the calculator. So this is what I would call X, plug it into the calculator. Then plug that in for Y. Okay. And if you're going to use Desmos to do this, I'm always careful with Desmos. And I can't remember, but a lot of graphing calculators, X is a reserved variable for graphing. So I would call it something else, like maybe H for the height is the 2,000 divided by the square root of 3. But it sounded like you used X, and it seemed to use it as a constant as well as a variable, and it seemed okay. But with some graphing systems, you got to be aware of that. Like the TI, don't do it on a TI. X and Y are reserved for graphing. Okay, so that was fun and exciting, wasn't it? If you didn't notice, a couple people yesterday had asked about question 10. Ms. Miller asked repeatedly, and I ignored her pleas. So I recorded a video for question 10. Question 10 is the fence leaning, the ladder leaning up against a wall that has to clear a fence that's a certain distance away. So I recorded a video of me going through that problem. So check that out. Does anybody need yet another day on this stuff? A couple people would like another day. Sure. I can move them both, but all right. So let's see. Drag and drop. 4.7, 4.8. I'll even move 4.9. How about that? And 4.10. Okay. And I'm actually going to move the final review over to Tuesday to put some pressure on you. Because the latest you can take the final is 10 o'clock in the morning on Thursday.
So I can take it at 9 o'clock in the morning on Wednesdays or what?
We'll have to check my schedule. I think that's okay. Those are my office hours.
10 o'clock Thursday?
Our official final time is 10 o'clock on Thursday, 10 a.m. on Thursday.
Done by?
No, that's the latest you can start it.
So we have to come in early.
I want everyone done by noon on Thursday. Because I got to grade and get my grades in by Friday morning. So. All right. So then I posted my Google Calendar here so you can take a look. And then just.
During your office hours, can I take the test then? Or?
You want to come in the morning?
Yeah.
Yeah. Wednesday, that's cool. I'll be here.
What about 10 Thursday?
What math are we math to?
10 Thursday is with the official time. So 10 o'clock on Thursday, I will be sitting in this room waiting for people to show up that haven't come already.
You know what?
Can we come
I could do
3 to
that.
5?
So
Daphne.
During when math 221
You-
takes their final?
211, yeah, you can come when one of the classes taking a final. That'd be okay.
Because I can't fit it in.
Yeah. So here's the deal again. This is my calendar if you want to take it from me. The testing center also has the final, and you can go take it from them if you wish. But the same rules apply. You got to make sure they're open, and it's got to be done before noon on Thursday because I got to start getting my grading done because that gives me only like 24 hours to get my grades in.
Do we have to take the test? Like the testing hours? How long does the test take? Like do you have like 1 hour?
If you're prepared, you should be able to finish the test in under an hour and a half. If you take extra time to check, then 2 hours is sufficient.
So we have 2 hours to finish the test?
Yes. Yeah. And the only reason you would get cut off is if you tried to go beyond, if you went to the testing center and they said, hey, we close at 5, give me your paper, please. right? And they
Just
will do
say I
that.
won't cut us off for 2 hours.
No,
Ooh.
So if you come before.
Oh.
they won't. But I would appreciate it if you wouldn't take all day to take the test. I think that's inappropriate. But I didn't set a time limit on it. I could if you want.
I think
No.
that's convenient.
That's
Just
convenient.
put that in.
Yeah, I
All
feel
right.
no pressure.
So let's move on and do some math. So we just took a quick look at one. So Vitor and Kate, you just came in. I posted a video solution to problem number 10 about the ladder leaning up against the wall. And then in the beginning of this video is the rancher fence problem, if you got stuck on that one. Are there any others we should look at before we move on?
No.
Silence on 4.8 for the moment. Okay, so I'm going to pick a couple 4.9 problems to look at, and then we're going to do, 4.8, and then we're going to do 4.9. So I heard from a couple people that 4.9 was refreshingly easy
Yeah.
compared to 4.8.
You mean 4.8 was easy?
Yeah, that one, 4.8. Sorry, I have trouble counting.
And did you hit the record button?
Yes, we've been recording for a while now. It says we're live, and
You're
we're
number
recording.
2.
Number 2. Yes, that is a beautiful one. That's one I meant to get to yesterday, but we ran out of time. All right, so let us grab that sucker and put it in a new place. Let's see, that's for the next stuff. Let's go here, blow it up. And it's time for more math. So when can you use L'Hopital's rule?
0 over 0.
Or
Infinity over
infinity, yeah. So if we plug infinity in here, we're going to get infinity over infinity. So that's the case we have in front of us here. So always check that you can apply L'Hopital's rule before you apply it. Other tip, if you apply it, you're creating an equivalent statement, but it's not algebraically equivalent. It's just equivalent according to L'Hopital's rule. So you should make a little note of that to yourself. So we're going to get the limit as x grows without bound of, what are the derivatives here? 8x, yeah, over 3e to the 3x. And then if we plug in infinity again, we get infinity over infinity again. So we can use L'Hopital's rule again. So let's do it.
I have a question.
Yes, sir.
So if you're to get an instance where it's like 0, you could use
0 over undefined is not L'Hopital's rule.
Okay.
Yeah. So do you have an example of that?
I don't know.
You don't know. Okay. Well, we can look at it in just a minute. So let's finish this one. So limit as x goes to infinity, derivative of 8x, 8, and derivative down here, 9x to the 3x. Oh, e to the 3x, sorry. And now if I go to plug in, I get 8 over infinity, which tends to be 0. Yeah, 8 over a really big number is pretty close to 0. What's that?
I said it.
Do you have a question?
Right. No.
Okay.
that's right.
Okay. Yeah, so the limit there is 0. So the cool thing about this example is what it shows is that an exponential function grows faster than a quadratic. If the quadratic grew faster, then the top would have overpowered the bottom. But here, the bottom overpowered the top. So exponential function grows faster than quadratic functions.
You could almost just look at it.
So you can pretty much just look at it now and say, hey, I'm pretty sure exponential functions overpower quadratic functions. And so, yeah, this is going to go to 0. Now, it turns out if this was a cubic, there would just be one more step in doing L'Hopital's rule again. If this was a 4th degree, there'd be one more step. So what if I did something like the limit as x goes to infinity of x to the 10th over e to the x? What do you think is going to happen here?
Well, it goes to 0.
You'd have to apply L'Hopital's rule 10 times, and eventually, so if we applied L'Hopital's rule 10 times, we would find this goes to 0.
Cool. Read number 5.
Hang on, I want to take a look at the one Sam was looking at because he had a question. What was it?
The limit as x goes to 0 of 2x over the cotangent of x.
X goes to 0 of, repeat,
2x
2x
over the cotangent of x.
over the cotangent of x. Okay, so let's see. Ooh, cotangent I don't do very often. And then Sarah said number 5.
That would just be x over y.
So I can't do cotangent in my head, so I would have to rewrite cotangent as tangent. So it'd be 1 over tangent. Is that going to help here?
That'll be 32.
Actually,
No,
sines and cosines might be better.
if you just did the graph and you look at
Okay, let's look at the graph of cotangent because I can't remember it. I haven't looked at that in a long time. Cotangent of x, and let's see, what's x doing here?
it equals
X is going to 0. Okay, so, on the left side, we are going to infinity. On the right side, we're going to negative infinity. So was this a one-sided limit or?
no, it's a two-sided.
Oh, okay.
So you just can't use L'Hopital's rule on it.
Let's see, if we're on the right, so if we're on the right side, both of these are positive. If we're on the left side, they're both negative. Yeah, so either way, this is infinity over infinity. Yeah, so it turns out you can use L'Hopital's rule directly on this.
I just take it.
Wait, I don't get, how is the top infinity? Are you plug in 0?
Oh, shit.
Because
It's
yeah,
not.
the top.
Oh, I
the
lied. What
top's
am I saying? Okay. Oh, yeah, so this is 0 over infinity. Yeah, so L'Hopital's rule does not directly apply to that, so I have to manipulate this. So let's see, cotangent is what? Cosine over sine? But this is the reciprocal of that, so I would use sine over cosine. So this would be equivalent to 2x times the sine of x over the cosine of x. What do we get here? If we plug in 0, we get 0 on the top and 1 on the bottom, which is 0. And we don't need L'Hopital's rule. It's just algebra. Yeah. Okay, cool. That was fun. Number 5. Number 5, sine of 7x over the sine of 4x. Cool.
Do we have to word for these?
Yeah. So my work was algebra. So sine of, let's see, which one did I get? I got 7 and 4. So 7x sine of 4x. And if I try to evaluate this limit, I get 0 over 0, which means I can't apply L'Hopital's rule to it. Okay. So derivative of the sine is cosine, so I'm going to get 7 cosine of x according to the chain rule in the top. And then the bottom, I'm going to have 4 cosine of 4x. Limit
Did you say 0 over 0?
is still 0, and this is L'Hopital's rule. So now we plug in again. What's the cosine of 0? 1. 1. So this is now 7
Oh, it
fourths.
sounds, oh, okay.
So is it always those things?
What's that?
So is it always the numbers inside?
With the sine, yes. So if this instead, if we said, what's the limit of the sine of ax over the sine of bx, where a and b are non-zero constants, and we take the limit as x goes to 0, then according to L'Hopital's rule, we're going to end up with a cosine, b cosine, and that's going to be a over b in the limit.
But it works for every single thing from like cosine.
No. No.
Okay,
This is only for the sine.
what about like number 6 where it's the change?
Okay, let's take a look.
And then also number 7, the exponential.
I'm gonna do all your homework for you.
No, please
Okay.
want help, Gary?
Oh, fine. Okay, I'll help you out. Let me blow these up a little bit. All right, 5 more minutes, then we're gonna move on. All right, let's copy this sucker. All right, so this one here, if I try to cheat here, oh, my teacup's missing. Oh. Damn, gonna do math without tea. I'll try. Okay, let's see. If I cheat and plug in 0, tangent of 0 is 0. This is 0 over 0. Okay. So that means I can apply. Now, it doesn't make sense to say it equals 0 over 0 because 0 over 0 isn't really a thing. But it looks like it's the right form. Derivative of tangent
Secant squared.
is negative. No, it's positive secant squared. Secant squared of 8x.
8 times.
And, 8, yep. And then sine would be twice cosine of 2x, limit as x goes to 0. And the secant is what, 1 over cosine?
Yeah.
So when I plug in 0, this gives me a 1, and this gives me a 1, 2. So this is 8 halves or 4.
It's the same thing as Doesn't matter.
Excuse me? Oh, we didn't even need L'Hopital's rule for this. Check this out. I think. Is that true? Oh, maybe we do. I don't know. Let me see. I had a brainstorm here. But maybe it's just a quiet little rain. Limit as x goes to 0. Tangent is sine over cosine. So this could be rewritten as sine of 8x over cosine of 8x times the sine of 2x.
You still get 0 over 0. No, you don't.
Yeah, you do. Yeah, you still get 0 over 0. Okay. And then you would have to apply trig identities. Yeah, you could clean this up with trig identities, but that would be way more work. Okay, next.
Number 7.
All right, number 7 coming up. Okay, screenshot. All right, so if we plug in 0, we get 1 minus 1 or 0 on the top and 0 on the bottom. Yep, so this is a candidate for L'Hopital's rule, so always check first. This does look like 0 over 0. So then we just go for L'Hopital's rule. So derivative of the numerator,
E to the x.
e to the x, and the derivative of the denominator,
10
Three.
cosine of 10x.
10 cosine of 10x. Yep. And now if we plug in 0, we get a 1 in the top and a 10 in the bottom, because cosine of 0 is 1. So 1/10. Yeah, so the pattern is check to see if it matches L'Hopital's rule. If it does, apply L'Hopital's rule. It doesn't hurt sometimes to try a little algebra first, see what happens. Sometimes you hit a dead end. Sometimes it makes L'Hopital's rule easier. You never know. All right, new topic. So you get another day to get that done. We're going to look at a thing called Newton's method for approximating roots. And what it does is it uses tangent lines at a point to approximate a root. So this black thing is my f of x here. And I want to know what this x value is right here. But for some reason, I can't solve f of x equals 0, right? I know no way to solve it. So what Newton discovered is that if you just make a guess at that value, which the guess isn't too hard, you just plot some points to make a guess, you then take that tangent line, we can find tangent lines, right? And you just follow that tangent line down and see what its 0 is. Is it easy to find the 0 of a linear function?
Yes.
Oh, wicked easy, right? So now what's going to happen is that tangent line, most of the time, is going to get you closer to that root than your first guess. All of the time? No, not all of the time. Sometimes it will shoot you out further away. So there are hazards to Newton's method. So now I have this new x value. So this was my first guess. And usually we call the first guess x0. Now I have a second guess I'm going to call x1. And then we find the tangent line there. So I have a line. Come on, give me a line. Line. There we go. So then I go and calculate that tangent line. And this tangent line is going to get me a heck of a lot closer than I was before. And what happens is usually when Newton's method works, it works fast. Usually within 3 tries, you're like 5, 6, 10 decimal places within the actual answer. Okay? All right, so let's see how it works. How do we find a tangent line? Well, in this case right here, we have x0. we need to know what f prime of x is. So we calculate f prime of x, and we plug in our guess. That's going to give us the slope, right? Then to find the equation of a tangent line, we have our lovely equation y minus y0 is equal to m times x minus x0. Usually we put y1 and x1, but it doesn't matter too much. So would you agree there's some y0 that lives over here? Yeah, and I find that by plugging my x value into my function. So putting all of this together, what do I get? Well, I get that y is y minus f of x0 equals f prime of x0, that's the slope, times x minus x0. That's the tangent line, this one right here. Then we set it equal to 0. Well, what gets equal to 0? Well, on the x-axis, y is 0, correct? Yeah, so I'm just going to put a 0 right there and solve for x. So let's choose black. So that's going to give me, so y equals 0 here. So I have negative f of x0 equals f prime of x0 times x minus x0. Distribute to solve for x, or actually, you know what? Wouldn't it be nice to just divide that f prime over to the other side? Yeah, let's do that instead. So I'm going to have negative f of x0 divided by f prime of x0. So this is gone. On the other side, I just have x minus x0, right? How do I solve for x now? Just add that over. Okay, so I get the following formula for this next guy right here. That's going to be equal to the previous x value minus the quotient of the function value divided by the derivative at that x value. And this process is identical over and over and over again, right? So if I want like the third step down the line or the second step down the line, then the next x value is just going to be take the one before that and subtract this fraction, f of x1 over f prime of x1. And we just repeat that over and over again. So this is the formula right here. To find the third x value, I just do the same thing but plugging in the second x value. Okay? All right, so we're going to test this on a function that we know the answer to see how it does. All right. So f of x is equal to x squared minus 2 is the function we're going to apply it to. And I claim we know the answer to this, right? Because if we set this equal to 0, x squared minus 2 equals 0, x squared equals 2, so x is plus or minus the square root of 2. So we're going to use Newton's method to approximate the square root of 2. All right, so how does it work? Well, Newton's method says you need to know the derivative. F prime of x is equal to 2x. So then we make a guess. Well, let's see. 1 plus 1 is 2, so let's guess at 1, right? I don't know. So I'm going to say in my first guess, this is what x0 is. The better your guess is, the quicker this resolves, but I'm going to make a bad guess. Say my first guess is 1. And the formula is always just take whatever x value you're given and then subtract the function value divided by the function derivative at that same x value. So to get my next x value, I'm going to plug in my 1 here, minus, let's see, 1 squared minus 2 would be the function value, and the derivative would be 2 times 1. Cleaning that up a touch, we get 1 minus negative 1/2, which is 1 plus 1/2, which is 1.5 or 1.5. And then guess what we do next? We just keep repeating this process. So the next one's going to be 1.5 minus the function evaluated at 1.5. So 1.5 squared minus 2 over 2 times 1.5. You just do this over and over again. This is a good application for a spreadsheet. I'm going to whip out a spreadsheet in a minute. So what does this give me? 1.5 minus, let's see, 1.5 squared is 2.25, I think. 2.25 minus 2 is 0.25 over 3. Do I have a mistake here somewhere? Oh yeah, no, that's right. And, oh, what is that going to give me? That would be what, 1/4, so 1.1 minus 1/12 if we wanted to do fractions.
1.416
What is it?
1.416
416 into 6 repeats, right?
Yeah.
Okay. Are we getting closer to the square root of 2?
Yes.
Yeah, the square root of 2 is 1.4 something. And we made our bad guess of 1, and within 2 tries of Newton's method, we have 1 or 2 decimal places already. Okay, so I'm going to get the fraction version of this just for fun. Let's see, I would have to multiply top and bottom by 6 here. So that's going to be 18 minus 1, which is 17/12 would be the exact answer here. And I could plug that in again to get the answer. Now I'm going to just do something first. I'm going to clean this up a little bit by plugging in f of x. I'm going to get an algebraic version of Newton's method. That's a little simpler, I think. So this is x minus x squared minus 2 over 2x. Right? And I'm going to copy that to a new screen to clean it up. Oh, I missed. Try again. Ah, close enough. Page. And that is a square, correct? Okay, so let's see. If we clean this up a little bit, we're going to get x minus, let's see, what do I want to do here? I need a common denominator. So let's put 2x in the bottom, and then this would be 2x squared minus x squared plus 2. So what does that give us? 2x squared minus x squared is x squared minus 2 over 2x.
2x squared minus x squared is 2x squared.
Isn't it? 2x squared minus 1x squared
Oh, yeah.
gives you 1x squared, right? Yeah.
Just-
So slightly different version. I'm going to rewrite this one more time. I'm going to divide top. What's up? I got a sign wrong. Oh, that's a +2, isn't it? Yeah.
Well, you.
It's
Oh, yeah.
minus
That's a
No,
plus.
it's right down there. You just messed up.
Yeah. This is correct. Now that's correct. Okay, I'm going to screw with this one more time. So this is one version of a cleaned up Newton's method. Now this is just for this function, right? Every function is going to be different. Okay. But this has some algebraic significance that you might appreciate. I'm going to divide top and bottom by x. So if I do that, x squared over x is x plus 2 over x, all divided by 2. Okay, so let's see, how are x and 2 over x related in this situation? Okay, so remember, what am I trying to calculate here? I'm trying to calculate the square root of 2. Ultimately is what I'm doing with this problem. So if you take x and you multiply it by 2x, 2 over x, what do you get?
2x.
You get 2.
Oh, yeah.
Yes. Okay. So what this does here is this x value is your guess, isn't it?
Yeah.
So this Newton's method, what it's saying geometrically, it's saying make a guess at the square root of 2. So I'm saying g equals the square root of 2. Now, if I was right, wouldn't g times g equal 2? Okay. So if g times g equals 2, then g must be equal to 2 over g. That's that guy right there.
Okay.
So what you do is you take your guess and then you divide it into 2. These are two numbers who multiply together to give you 2.
Yeah.
Best case scenario is g is the square root, in which case these are the same number. So then what you do, what if you're wrong? Well, then you have two numbers that multiply together to be 2, and then you average them, and now you get a better estimate at that square root. Okay, so I'll show you another situation that involves. Consider the square root of 12. Okay, so 3 times 4, 3 and 4 are pretty close to each other, aren't they? Yeah, so I'm going to guess that 3 is the square root of 12. Okay. Now, what happens if you take 12 and you divide by 3? What do you get? 4. Okay. So now if you take 3 and 4 and you average them,
6.
you now get a better estimate at the square root of 12. So what's 3 plus 4?
Oh, wait, 7.
7 divided by 2
7 times.
is 3.5. That's a better guess at the square root of 12. You see the geometry of it there?
Does that work with that rate? Like square root?
Yeah, so bottom line, this works for anything. So if you wanted to know what is the square root of, let's call it b, then you just make a guess at it. Then you add to that guess b over your guess, right? That's what I did right here. And then you cut it in half. Now you have a better estimate at the square root.
And
Repeat
so,
that process over and over again.
As soon as your estimate starts getting extremely close to
Yeah, so let's look at this in a spreadsheet just for fun.
but like the closer that your estimate is getting to the answer that you're getting closer to the
Actual square root.
answer.
Yeah, watch how fast Newton's method works. So basically that geometry idea I showed you just right there, turning rectangles, what I'm doing is turning rectangles into a square. That's Newton's method in action for square roots. So let's get a new Google Sheets, move this up a little bit. So I'm going to use this for the square root of 12. So I need a guess. Okay. We'll call this 0, guess 0. How about that? And my guess 0 is 3. So then my next guess, the process is to take your previous guess, add to it 12 over that guess, and then cut that in half. And then just repeat that. Okay. So this is Newton's method twice, 3 times, 4 times. And then over here, I'll say, what is the square root of 12? Look at how fast Newton's method got there.
That's impressive.
Dang.
That is pretty impressive.
So at that point, you should be able to plug it into that, and it will give you the exact same answer as your estimate.
To this, yeah, so if I went and did it a 5th times, to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places, I can't do any better. Now, there are calculators that do better than 9 decimal places, in which case you would see that these two numbers aren't the same. They're a little bit off. But Newton's method, if it works fast. Okay, so let's do it on a different example. Did you have a question, or are you just
No, I'm just trying to.
hanging out there? Okay.
So if it doesn't work, does it mean it doesn't work slowly?
If it doesn't work, it either does a loop, like you go like 0, 2, 0, 2, 0, 2, or it just heads off to infinity. It goes wham, and it just disappears on you. Yeah. So Newton's method either works really quick within like 4 steps, and you're like within 10 decimal places, or it explodes pretty quick, or it does a weird cycle somewhere. Yeah. But more often than not, it works really quick.
With the check again.
And to check it, you just take that number and plug it back into the original equation, see if it works. Yeah. So like for us, we were trying to solve the equation. Well, let's see. Let's go back.
X squared minus 2.
Let's see. The last version for square root of 2 we got was 17/12, which is not too bad. And if I plug it in here, what happens? So calculator, spreadsheets calculator. So if I take 17 over 12 and I square it and then I subtract 2, I should get a number that's pretty close to 0. 1 or 2 decimal places from 0. If I took it out another step, I'd be even closer to 0. Okay. So Newton's method works fast. All right, so I forgot my notes along with my T somewhere in this building, so I'm going to look up a problem from homework. And I know, ooh, sine of 2x. Let's do that one. This one, ooh, seventh power.
So those x to the second one, would that just be the second time you've done it? Or is
Yeah,
it-
so this is the first time you've done Newton's method. The second time is the third time. Yeah, and spreadsheet really is the way to go on this.
So we can use.
Because once you type it the first time into a spreadsheet, you just fill it down, right?
That feels like cheating though.
Well, we could do the same thing in Desmos. I'll show you how to do in Desmos. What's up?
Can you show me how the spreadsheet works? I tried following along.
Okay, yeah, I did that quick. So I'll do number 2 on a spreadsheet and in Desmos. Okay, so I love spreadsheets. They're like the greatest thing ever. Next to calculus. Oh, that reminds me. Somebody showed me a cool calculus song you guys got to check out.
Oh wait. Okay, wait. Is it that one?
It's Bohemian
Yeah,
Rhapsody.
That's what it is.
You've
yeah.
already heard it?
I don't think I said that to this group chat, but they
Yeah, we
were
have-
like,
we
I'm
have
not
our-
gonna listen to it.
I didn't listen.
Well, no, I already listened to it because
I thought it was cute. Look it up. Look up Bohemian Rhapsody calculus on YouTube. It's awesome.
So great.
I have a link up.
No, it's really great because I'll listen to it probably about every 2 weeks and I'll start to understand
Yeah.
about it even more.
Yeah, there you go. All right, so this is my f of x right there. Oops, f of x. We need f prime of x next. So
Why did you
f,
skip the sine one?
I'll go back and do that
Okay.
one if I have time.
Daphne's offended.
So this is going to be what, 14x to the 6th plus 16x to the 3rd. Okay. And then Newton's method, I'm going to ignore the subscripts for a minute. Newton's method says, so let's call it NM for Newton's method, says pick an x value, subtract from it the function over the derivative. So 2x to the 7th plus 4x to the 4th plus 4 divided by 14x to the 6th plus 16x cubed. Now, this is a sufficiently complicated function that this probably isn't going to simplify much. So you could try, but don't bother. This is good enough right there. Okay. So this is what Newton methods tell me. So the next thing I do is I'm just going to plug that thing into either Desmos or a spreadsheet. Okay, so I'm going to do the spreadsheet version first. And let's see, they told me to let x1 be 2. So spreadsheet. So x1 is going to be 2. So then underneath that, I'm going to type my formula, which is just equals. And instead of an x, I'm just going to click on the number above. So there's my x minus, and then start parentheses for the numerator. So that was what, just, was it 2x to the 7th? 2, and a spreadsheet, you got to go times, otherwise it'll scream at you. So 2x raised to the 7th plus 4 times x raised to the 4th plus 4. Close your numerator, divide, denominator is then 14 times x, and don't forget your times, to the 6th, plus 16 times, there's my x, raised to the 3rd. Close parentheses, hit enter. There's my next answer. There's the one after that. There's the one after that. What should happen is, ooh, this one didn't resolve as quickly. Oh, no.
Did you mess up?
No, this is one of those situations that's going to cycle out of control on us.
But it only wants the.
Oh, you know what could be happening here? It could be that we don't have, that if we had a calculator that had more decimal places, it might actually work.
Okay. Why?
Oh,
But it
it's like
jumps to -4.
it goes from that to negative 4. Yes.
You get to 0 and then it jumps to -4.
Yeah, so
But maybe it's not asking for an answer. Maybe
It's
just
not
wants
asking
the
for
one
an
and
answer.
two.
yeah, it's asking what the next couple
It's like-
are.
It's,
Yeah, I
it's
wonder,
the
can I
second and
just-
the third.
Can I copy and paste in there?
Yeah,
Ooh,
except if you got all of them.
Yeah.
One.
Yeah, you didn't select. You
Oh.
It's like the entire.
Yeah.
I
You
did,
didn't
oops.
specify it.
Oh, gosh.
I want all the answers.
Oh, look at that, isn't that sweet?
Ooh, is that a test?
Sure.
You just had to do it on Desmos too.
Ta-da. Okay, Desmos. So Desmos works the same way. This time I'm going to call it n of x, n for Newton's
Oh,
method,
that's cool.
equals, and then type it in just like we did, x minus fraction, and then it was 2x raised to the 7th
Plus 4x.
plus 4x raised to the 4th plus 4 divided by
14x
14x raised to the 6th
plus 16x.
plus 16x to the 3rd. So then there's two ways to proceed from here. One way is to just type n and enter your number. Now, to get this number in here, you have to assign it to something. So you have to say, okay, let that equal m. Ooh, I didn't like that. I have to go the other way. Let m equal that number. There we go.
Yeah.
Okay. And then you go, okay, what is n of m? And then you could say, okay, let that be LMNO. Oops, O. And then if you needed another, you'd say, okay, what is n of O? Otherwise, you have to type in what you see there. And then you're introducing rounding error, but there's a sufficient number of decimal places there that rounding error is probably not a big deal.
Why can't you do a table?
The problem with doing a table is Newton's methods is what's called a recursive function,
So-
which means it's not depending on the number to the left, it's depending on the number above. And a spreadsheet does that naturally, but a table in here doesn't.
This Desmos not have a spreadsheet.
Desmos does not. GeoGebra does, but Desmos does not. Yeah, this Desmos does not have a spreadsheet version. Yeah, so it hasn't caught up to, and it may decide to never do a spreadsheet function. All right, let's go back and do the sine in the last few minutes, and then we can do more of these tomorrow. All right, so we have twice the sine of x equals x. Okay, so I got a little work to do on this before I can use Newton's method. Twice the sine of x equals x. So to solve this for Newton's method, I got to get 0 on one side. So then I would say, okay, take twice the sine of x, subtract x equals 0. So once I have 0 on one side, then I can say, all right, this thing over here, that must be my f of x. So Newton's method is for finding zeros of functions. So you have to get a 0, then see what your function is. Next, we need f prime of x, which would just be twice the cosine of x minus 1. And just keep in mind, there is no algebraic way to solve this equation. Okay? And this one back here, under special cases, 7th power polynomials, you can find roots, but most of the time, there's no algebraic solution.
Only for 7th?
Well, I think somebody proved a while ago that after the 5th power, you can't find algebraic expressions for in general for any other higher polynomial. That's my recollection. That's what somebody proved last century. It was a couple. It was like 2 decades ago. Somebody proved that. Yeah. Okay. So so back in the days of Newton, the quadratic formula existed. The cubic formula did not exist yet, is my recollection. And the quartic formula definitely did not exist. That didn't exist until like the 80s, I think. Anyway, all right. So Newton's method then says to take an x value and subtract from it the ratio of the function, which would be twice the sine of x minus x over the function's derivative, twice the cosine of x minus 1. So that's Newton's method there. Then you decide whether you want to just use a hand calculator or Desmos or a spreadsheet. Okay. Personally, I love a spreadsheet for this because spreadsheet is great at recursive problems.
Excel will do trig functions?
Yes, I believe so. So let's take a peek at that. So what did they tell me to use first guess for this one right here? They said use x equals 2 as the first guess. So new sheet, put the first guess at the top, and then under that just type equals, And every time you need an x, just click on the cell above. Minus, here I need parentheses, and then this was what, twice the sine, and yeah, it does have the sine, and it only works in radians, notice, which is good, of the x value, minus the x value, close the numerator, divide parentheses for the denominator, twice the cosine of the x value, close the cosine minus 1, close parentheses, and then the cool thing is once you type it, you just go ba-ba-bing, and hey, look at that. After the 5th time, it runs out of accuracy. It says, this is the best I can do.
So can we make a program, use a program for that? Oh, that's
Could you write a program to do this? Yeah, you could write this in Scratch. Totally.
Can you go back?
Yeah.
I just want to
Do
see
it and then just send us all a link.
Back here or back to my spreadsheet formula?
Somebody,
The spreadsheet formula?
Somebody
Okay.
make a TI program and just bring in their transfer cable on
Yeah.
Wednesday.
Yeah, so instead of an x, my variable is a1 here.
Somebody just write the program, just give it to all of us. Yeah.
I need that program.
Yeah, you could write a program. Let's see, could you? Oh yeah, you could write a TI 80 something program to do this.
Yeah.
Because TI will, it doesn't do. Oh, can you do that?
Yeah, I think you could.
I think it has a derivative, a numerical derivative function. I mean, it can't do a symbolic derivative, but it can do a numerical derivative. Yeah. Oh, you could just type you could like say y1 is the function, y2 is the derivative.
Like have the person.
Yeah.
Plug in the derivative and
Yeah. So yeah, you could program this on a TI calculator. Yeah.
Whoever does that, bring in your
Yeah,
transfer cable.
I remember
please.
when I first started teaching calculus, the TI 82 had just come out, and some of my clever calculus students
Is that
were
the
programming.
boxy one?
What's that?
Is that the gray boxy one?
The 82 is gray and boxy. The 81 came up before that, and it could do less, and it was blue.
I think I have a TI 82.
Yeah, I have an 81 somewhere. All right, we're out of time.
On the TI-84,
For fun with math.
informed.
Have a good day.